All right, this video is about the entropy of the universe with the symbol S subscripted uni. I'm Dr. Ryan Hayes from Andrews University Chemistry Department, and we're going to learn a little bit about the entropy of the universe coming from the 3 laws of thermodynamics. The first law states that you can neither create or destroy energy, you can change it. Second law is a spontaneous process results in the increase in the entropy of the universe. There's our connection right there. And thirdly, the third law, the entropy of a perfect crystal at absolute zero is exactly 0. So the entropy of a perfect crystal is 0 at absolute 0 Kelvin scale. What are these things in particular? We're mainly going to focus on the second and third one, but really the first one is about changing energy. It could be the chemical energy, electrical, heat, these things as you transfer them, you're going to create or destroy. Now you're going to change form, often lose energy and friction in these things. But there is a mathematical representation of a chemical reaction that deals with entropy. See, the entropy of the universe in the second law helps us to describe whether a chemical reaction is going to take place or not. That's really important. That's really what we're after. Can a reaction take place? And the second law says, yes, it can if it's spontaneous. And so we want to try to find these spontaneous chemical reactions. Those are the ones that are likely to work. We need 2 things in order to figure out the entropy of a chemical reaction. That is the entropy of the system and the entropy of the surroundings. We're going to talk more about that. And then the third law, the way to really think about that one is you have perfect crystal, all the atoms are perfectly lined up, and it's at super cold temperatures, 0 Kelvin. That is 0 entropy. And anything warmer than that, less orderly, it's going to have entropy to it. It's more spread out. We had more about that in another talk with entropy in a nutshell. Okay, second law of thermodynamics gives us something to work with, quantitative, that we can actually make some calculations. But we need to know 2 things now: the entropy of the system, entropy of the surroundings. If we can calculate those, we can see if S of the universe is positive. It means it's increasing. This is going to be a spontaneous chemical reaction. So that's really great. Now the entropy of the system, we already know, as I mentioned, we can go calculate that from some tables using the summation method, and more in my video entitled Entropy in a Nutshell. That'll help you figure that part out. So the challenging part actually is the entropy of the surroundings, because that's not the chemical reaction we're dealing with, it's everything else. Is there a way to approximate that and understand it in a way that we can deal with it simply? The answer is, of course. We're going to have to make some thoughts, though, to make this connection. So the entropy of the surroundings then is going to be related to our chemical reaction. How is that? Well, because the chemical reaction can produce heat or take away heat from the surroundings. So it's really the enthalpy, that's the key thought, that starts to connect. The heat flow of the chemical reaction is the connection to our surroundings. So there's 2 aspects to this. What is the temperature of the chemical reaction that's taking place? And what's the flow of the heat? Is it leaving the chemical reaction? Is it coming in? Is it exothermic or is it endothermic? So one of the things we need to also think about is not only just heat flow, but why are we dividing by the temperature? Why are we dividing by K? A little thought process may help us here. If I had some penguins in Antarctica, or let's say I'm building a fire, and I'm going to put it on, or near the penguins, don't want to put it on the penguins, or I'm going to put it on the sun, assuming I can survive that. Where would the heat of that fire have the biggest impact? With the penguins or with on the sun? Pause and think about it. A, B, what do you think? I don't think it takes much thought to go A, of course. That's going to have the greatest impact. If I'm going to build a fire, the heat of that fire is going to have the greatest impact. So the lower the temperature, the bigger the impact. That's called an inverse relationship. So that's why we're going to end up dividing by T to get this inverse relationship between temperature, absolute temperature in Kelvin, and the entropy of the surroundings. So because of that, scientists then have been able to make a replacement for this delta S of the surroundings. We can replace the entropy of the surroundings with heat flow, which is just entropy that we know. We're going to call this the enthalpy of the system, which we know is enthalpy of the reaction with the subscript R, or sometimes just delta H. It's all of that. That's the enthalpy of the system. So we can replace now the surroundings, the delta S of the surroundings, with negative delta H of the system, the enthalpy of the system, divided by temperature. Well, wait a second, where'd that negative come from? Well, because if it's an exothermic reaction, it's going to produce heat to the surroundings. That's going to increase the entropy of the surroundings. That's a positive number for the surroundings. So we're going to have to do the opposite sign to get us the right calculable number that represents entropy. So a couple notes here. So the entropy of the surroundings then is approximated with the enthalpy of the system, because that's really what we know. If we're dealing with a chemical reaction with hydrogen and oxygen and water or whatever it is, we know what the chemicals are of the system. That's why it's important that we find a replacement for the surroundings, because it's everything. And we can't possibly know the entropy of the surroundings if we don't know what everything is. So making the switch is very important. So the inverse relationship, that's also a key thought there. And don't forget, this is in Kelvin. T, capital T is in Kelvin. That's the absolute temperature scale. We're never doing it in Celsius or Fahrenheit. Those have negative numbers. They give you sign flips. It's much easier to always think about Kelvin, because it's a measure of the energy that's there. So we don't have to worry about any tricky sign flips coming from a negative Kelvin. All right, so now we have this new equation here. And we can have, so we have the delta S of the universe, entropy of the universe. We can calculate this now by going to a table and calculating delta S. A couple of key thoughts though. The entropy of a system is either a positive or negative number. Same with the enthalpy. It also can be a positive or negative number. So this really gives us four options that the entropy of the universe can be depending on what type of chemical relationship, chemical reaction that's taking place. So important to note though, that when we talk about the entropy of the system and the enthalpy of the system, these guys are not related. No connection. We have to use two different thought processes for entropy. Is it spreading or coming out together? Enthalpy, is that reaction producing heat or is it taking heat in? So those are our key thoughts that we want to keep track of. Okay, so four options for the sign for calculating delta S. There's only four. So you can see them here, that if our surroundings has a positive number for the system, then we're going to have a nice spontaneous chemical reaction, and it doesn't matter what the temperature is. Now, if the system and the surroundings are both negative entropy, then you're going to have a negative entropy for that chemical reaction. And it doesn't matter what the temperature is, it'll never be spontaneous. These two other situations where you have difference in signs, you're going to get a difference in, you're going to have a temperature dependence now on the entropy of the universe. So that means there's a temperature at which things will go from being spontaneous to non-spontaneous, back and forth. All right. So we could actually calculate that. Well, what do you mean? Well, if you're going from a positive number to a negative number, that means you're going to go through zero. And zero is that transition temperature. So if we plug in zero for the universe here, we can run through a quick calculation here where we replace the entropy of the universe with zero. And if we know the delta S of the system and then delta H of the system, we can go look these things up in tables. I can add delta H divided by T to both sides. That gets rid of my negative. And then solve for T, put it on one side, divide by delta S. So this gives me a little formula to actually figure out what temperature the chemical reaction that is temperature dependent will go from being spontaneous to non-spontaneous. Okay, so that's very important. So this actually comes into play when we're dealing with phase changes. This is one of the key temperature dependent chemical reactions that we like to study. So there's a temperature at which phase changes going from being non-spontaneous to spontaneous. And that actually, those temperatures are called the boiling point temperatures and the freezing point. So if you know what the enthalpy of vaporization and the entropy of this vaporization, you can actually figure out the boiling point. So these are things you can go look up in tables and calculate. And then it gives us an opportunity to think through the sign, because these things are both going to be, enthalpy and entropy would either both be positive or negative numbers here, so that they cancel out and you always get a positive calculation for your temperature. Let's do a practice calculation. All right, let's say we want to calculate the temperature for the phase transition for water as it goes from liquid to gas. Hint, hint, this is the boiling point, 100 degrees Celsius, 373 Kelvin. Let's see what these numbers do when we look them up in some tables. So let's calculate delta S for the system here. How do we do that? We go look it up in a table. And so here I have my magic table pop up. I have entropy numbers for water as liquid, for water as a gas. I have enthalpy and whatever this delta G business, Gibbs free energy. That's going to be discussed in another video. I can calculate the entropy of the system by summing up the products and entropies minus the entropy of the reactants. I simply have one product and one reactant. I subtract it, and I get a positive 118.9 kilojoules per Kelvin. Units are very important. So this is a spreading out, very positive entropy. Entropy is going to help push and make this happen. All right, but what about delta H? Is this going to be an endothermic or an exothermic reaction? You should think about that and know that. Let's see if the numbers give us. Same kind of calculation, but this time we're using the enthalpies of formation of the products minus the reactants. Plug in the numbers from the table and you can see I get a positive 44.0 kilojoules per mole. This guy is an endothermic reaction. You got to put heat in to turn a liquid into a gas. That should hopefully make sense. All right, but let's put these two guys on the same units. I'm going to go ahead and just switch the enthalpy into joules, multiply by 1,000. Now I'll plug it into the T equals delta H over delta S equation. My joules will cancel out. I'm left with Kelvin on top. 44,000 divided by 118.9, you can see 370.1 Kelvin. What is that in Celsius? Well, if I subtract 273.15, I get 96.9 degrees Celsius. Oh no, that's wrong. The boiling point is 100 degrees. Let's throw this whole thing out the window. No, that's not how it works in chemistry. Enthalpy and entropy, these numbers are taken from calculations, from measurements. They have error associated with it. So let's not freak out. It's actually pretty close. So roughly 97 degrees Celsius. On the big scale of things, this is not too far off. So given the error that's in there, we actually were able to calculate the boiling point within a few degrees for water, understanding just the entropy of the system and the enthalpy of the system. So this is pretty good. So kind of in summary, we can understand now the entropy of the universe if we think about it in terms of the two available signs there are for the enthalpy and for the entropy. And phase changes end up in this temperature dependent realm here, this third type of reaction, because there's 4 different types of chemical reactions. And so now though, we can turn the second law into something usable for us in the chemistry world. And so it helps us to understand how to take some numbers and tables for a chemical reaction and make an interesting prediction of whether the reaction is spontaneous or not, and if it's temperature dependent, where is that temperature at which it becomes spontaneous. So we got a lot of things out of the second law when we turned it into equation. Thanks for joining me on this entropy of the universe talk. Hopefully you've learned a few things and how we can understand this in relationship to chemical reactions.